Welcome back to another video in Code 01. So today we're knocking out some big O examples. So yesterday's video we started to handle with what is big O, what are algorithms, how do we use them, why do we even need to know them, some graphical instances showing you the differences between things like a big O of constants, big O of n, a big O of log, and then we got even to cubics and squares, and just to kind of get an idea of where these things lie in terms of how computationally intensive they are, either in terms of time and or space. So some more examples for today. So big O examples. First, for a big O of 1, a constant number. So we have here creating a function. Function is constant. We're going to put values as the argument. All we're doing is printing, in this case, the first item in a list of values. How do we know it's the first item? Because we're indexing at 0. It's going to be our first item. So we're printing out values, whatever we're going to run through values as the argument, and printing out the index of 1. So we're calling that function here function constant 1, 2, and 3. So out of this list, that was what we're passing through our function of function constant, give me the index position of 0. And sure enough, it gives me 1, because that's appropriate. Now, the point of this is that it doesn't matter how large my values list becomes. This values list, I could have made this and I'm still going to get 1, because it doesn't matter if this was infinity digits long, I'm only grabbing the first index position, which is always going to be 1, and it's also in the first spot. So this algorithm is only going to grab the index position 0 in that list, no matter how many times I run it, no matter how big this list is. So this is a constant. This is a big O of 1. And constants, as you remember from the chart from yesterday, have one of the lowest computationally intensive impacts on a computer system in terms of performance. So scalability, this is nothing. This is easy as balls. You could scale this as much as you want. We're only grabbing the first index position. So now we're going to move on to O n, big O of n, which of course is going to be linear. It's not a constant, it's linear. So linear is slightly above in terms of we're still in good performance on a big O performance chart. So regardless of n, we still can get fair computational intensive out of the system. So here we're defining a function, and we're going to put a list through there. So we have for val in list, so that's going to be for our values in a list. We want to print the values. So it doesn't matter what our list is going to be, it's simply going to print this. You know what I'm going to do? Let me do this just so you guys can see the outputs as we run it, so I don't want feel like your brain is cheating. So here I'm going to pass the list of 1, 2, and 3 through my function list defined function, and all it should do is print out each one of these values within the list. So we're going to shift through there. So of course it prints out 1, 2, and 3. So for every value is going to print in the list. Each time the list gets larger, though, what's going to happen to our and it's also going to get larger. It's not going to be a constant. It's going to be linear. So if right now if it's 3, it's going to print out 3. Conversely, if it was larger, it would print out a larger list. So our list growth does have an impact on the computational intensive of our system, and it has a computational intensive risk of, so you'd say big O to the n. It has a linear growth rate. So as our list grows with this particular function, as our list grows, so too does the computational. Not to the point that it's disastrous, though, because again, computers can do a hell of a lot of math. But again, the point is it has to do the whole list, whatever I do pass through here. So that's why O n linear is going to be a little bit more computationally intensive than O1 constant. So what do we have? Every value will print the list each time, so the larger the list gets, the bigger the big O. Yeah, that's exactly what we just covered. So now we're going to go to quadratic. So this is going to be O with n is squared. So we're going to create a quadratic big O function. So in this case, we're going to do that just by doing a for loop in a for loop. So we're going to do a functional quad. We're going to have a list. And what we want to do is print a pair. So for item 1 in list, and then for item 2 in list, print item 1, print item 2. Nothing crazy. We'll make our list just for fun. We'll make it a little bit bigger. I want this to be neat. And then we're just going to call our function quad, and then put our list through our list that we produce of 1, 2, 3, 4, 5, 6. So what this is going to do, it's going to go for item number 1 in the list, and then it's going to print 1, it's going to print 2, it's going to print 3, it's going to be 1, 1, 1, 2, 1, 3, 1, 4, and it's going to do this for each item in the list as it goes through list 1 and list 2. So sure enough, we have 1, 1, 1, 2, 1, 3, 1, 4, 2, 1, 2, 2, 2, 3. We're never dropping anything off 3, 1, 3, so it's creating a pairs list all the way through this. But the point of the matter is that this is going to be one iteration for the computer system. for number one, let's just take one element within our list. So for the first element, it has to do this run, and then it has to do this run. So it has to do n times n for each element that's in our list. But this doesn't matter how big this is. It doesn't matter if this is one number or one element. It doesn't matter if it's a million elements, infinity elements. The point is it's always going to have to do n times n. So that's how we're getting our n squared. That's going to result in this. So that's exactly what we're getting from. We're going to have a quadratic representation of this on the graph, which, as we saw from last week. Let me bring that up. When we get into quadratic, again, we can see that as the elements grow very quickly, let's say, we're at 0 and then 1 and then 2, as our elements grow, as our n grows, the operations are going to be, in this case, exponential, because we're n squared. It's because we have two loops, one less inside the other, as we said. For a list of n items, we also perform n operations for every item in the list. That means a total will perform of n times n assignments, or n squared. So if we have 3 assignments, let me show you. So if we only have, here we have 6, so we should have 36. So if you counted this down, 1, 2, whoops, you should have 36. So let's keep this a little shorter so it's easier to see. So if we have 3 elements, we should have 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's our n times n, or n squared. Whatever our n is, it's going to be n squared in terms of the computational intensive for that particular system. How many operations are we actually performing? We're performing this n operations for n operations in a loop of loops. And it says you can see how very dangerous this can be for very large inputs. This is why big O is so important to be aware of when you're creating software. Hence, the input of 3 gives us 9 outputs. That's what I just showed above. We have 9 outputs for an n of 3. Calculating scale of big O. So insignificant terms drop out of the big O notation. And this is exactly what we saw yesterday when we did... Nope. Here we go. In terms of, these are called insignificant terms, the 45, the 20, the 19, but you're always going to go in a backwards order, meaning that the lowest term is going to be the 19, and then it's going to be our square, and then it's going to be our cube, in the terms of the constant that stands before them. So as you saw, just going from a big O of 1 to a big O of 2, our 19 started to become very insignificant. And then from a big O of 2 to 10, not only did our 19 become insignificant, but so too did our 20 and our 45. What came significant, though, was the cubic. Even our square started to show that it was falling off rather quickly. So as the n increased, that n squared is going to become smaller and smaller compared to what the cube is going to contribute to the ultimate outcome of your answer. So when it comes to the big O notation, we only care about the most significant terms. Remember, as the input grows larger, only the fastest growing term will matter. This is, again, like taking the limits toward infinity if you're familiar with calculus. So that's what we always want to focus on. What is the most significant term? And that's what we were hitting on here. Out of this whole function, this is the most significant term, because as n grows, this is going to contribute the largest to the overall answer, in proportionate to the other values that would reside within that function. So here we're creating a new function to find print once, and it's going to print all the items once. So for the values, or for a val in list, print the val, print list, print once, and then we're just going to call our list. So what list is this? Well, it's going to go by our last list that we ran in the Jupyter notebook, so it's going to be list 1, 2, and 3. So if you wanted to see that, you could also run it. It's going to print the list 1, 2, and 3. So we can see how the growth is linear for this particular input. So this is just going to be, since it's a linear growth, it's going to be big O to the n. And you'd say, yeah, that makes sense, right? For every value in the list, if there's 3, we're only running this n times. If n is 1, we're going through this once. If n is 2, we're going through it twice. If n is 3, we're going through it 3 times. So it's a linear growth rate for the function that we're dealing with in regards to big O. Here we're defining print 3. We have our list, but now what we're doing is we're printing it 3 times. So for each value that's in our list, we're doing it 3 times for each particular n. So for our list, it goes through print value in the list, it's going to be 1. Print value in the list, 2, 3, 1, 2, 3, 1, 2, 3. It's just printing this 3 times because, again, that we have 3 different for loops within our function there. So again, this is going to run 3 times for each of the n's. This becomes an order of 3 times n. Now notice it's still linear. It doesn't automatically becomes n cubed. That wouldn't make any sense because each of these are going to be run in a sequential fashion, so it's just going to be 3n, but it's still linear. The important thing here is this. 3 times infinity is not really different than infinity, so we can drop the insignificant constants, and that's why this 3n, you'd be technically correct to say this is a big O of 3 to the n. As n grows, our computational tense is going to be 3 times that n. However, as n becomes infinity, the 3 becomes inconsequential, becomes an insignificant constant. So this would be a big O of n. So this is no different than this would be in terms of its big O notation. Granted, would you say this is going to run faster than this? Absolutely. But we're talking very small lists right now. When we get to very, very large lists, those times this should still always be longer than this, but it becomes inconsequential in terms of the difference. And here we have a new function. We're defining the comp. It's going to take a list as an argument. So now we're doing 3 different things, and you can ignore this right now. Let's just go down and see what we're doing. So we're printing the list of the first position. That's all we're doing first. And then we're creating a new variable called the midpoint. We're going to take the length of that list and divide it by 2. And then we're taking a for loop for the values in the list from the beginning to the midpoint. Print that value, and then for x in range 10, so we're going to go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, print the number. So I'm going to shift enter through that so it can actually create its part. Auto saving. Oh, Jesus Christ, I never called. I'm like, why is it running? I never called my actual function that we created. So here I have my list. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then I'm calling the function we just wrote up above. And I'm passing through this variable. So now we have 1, 1, 2, 3, 4, 5, and then we have the word number printed 10 times. So what is the big O of this particular function? So if we're looking through this, again, you might recall this from yesterday, all we're doing here is taking our list that we have here and pulling out the first indexed position. That's going to be a constant of 1 always, right? It's our big O of 1. That's a constant. That's what we have here. This first function is going to print a big O of 1. This is going to be a constant, nothing special there. This is just creating the variable midpoint. We're taking a length of the first dividing by 2, and then we're using that in this piece here. So what we're doing is, all we're doing is printing the first half of the list. So we're from the beginning of the list to the midpoint, print those values. So if a list of 1, 2, 3, so the midpoint you're going to tell me is going to be 5. So go from the beginning, because it's 10 divided by 2 is 5, and then go from the beginning of the list to the midpoint, it's going to print 1 through 5. That's what it's going to do for this point. So for this one, this is going to be, that's what we have here. We're only doing half the list. So it's big O n divided by 2. Because whatever my n is, here my n was 10. So the big O is n divided by 2, it's 5, because we're going to have an output of 5 different elements. And then for the last one, for x in range 10, so we have a constant here, right? Doesn't matter what this is, constant, all we're doing is printing in numbers. This is going to be O to the 10 to big O of 10, or a big O constant. So what we have here, we have O1 constant, we have O n over 2, and then we have big O 10, which is also a constant. If we were to compare all three of these, that's what we're doing down here, we have big O1 plus n over 2 plus 10. What did we say, though, about constants? Constants are going to fall out as the n gets larger and larger and larger. As we're scaling up, you're going to see how the number 1 and the number 10 are going to quickly mean absolutely nothing to our overall answer for computational intensive on a big O. And even the divided by 2 is going to begin to have no effect either. So what we're going to be ending up with is a big O of n. This is also going to become a linear growth rate based on the n, because the constants, although they do have a mathematical impact early on, that impact falls off dramatically as we scale up. So another piece that we're going to speak about when we get to big O is, and talk big O notation, in computational intensives and algorithms, is worst case versus best case. Now, there's no point in really computing a best case other than knowing what your best case could possibly be. But it's best to do your big O notation in a worst case scenario. So that's why we're usually concerned with the worst possible case of an algorithm, because then you know what your worst case scenario is going to be and you can work up from there. But in an interview setting, it's important to keep in mind that there is a worst case and a best case scenario, and they can have very completely different big O times. They should have very completely different big O times. So what we're going to do here is we're going to create a best case scenario first off. So I'm going to create a function. I'm going to call it matcher. It's going to take a list and it's going to take a match. So we're having two different arguments. So we're going to pass through this function. And then for item in list, for item, if item equals match, return true. Otherwise, we're going to return false. We're going to follow the loop. So I'm going to have a list. We already have a list produced. I have LST here. I'm just going to run this cell to see what our list is. So it gives me the output. Our list is 1 through 10. All right, sweet. And then what I'm doing here is I'm calling the function which create a matcher. And I'm saying for the first argument, it's list. So that's what I'm putting through here is list. And I'm putting a number 1, so a match of 1. So what it's going to do is going to say for item in list, for number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If item, if this equals the match, and the match here, that was our argument. Here's match, here's my argument. If any one of these equals this, it's going to return true. Otherwise, return false. So it doesn't say, it says if any item essentially is what we're doing in that list. So what do you think we're going to get for this one here? Well, we're going to run it, and we're going to get true, because sure enough, within this list, there is a match for the number 1. Now, the reason that this is a best case scenario is because where is the number 1 that we're trying to match? It's in the index position of 0. It's at the very, very first of our list. So a computer is going to go sequentially when it's dealing with a list. Or, when we get to different kind of algorithms, you can see, you could say, oh, we could split it, we could do higher, lower, and go from there and just break it down half and half and half and half. But in this particular example, our list, what we're matching is the first element. So the list goes, is number 1? Yep, true. That's our bet. So the time to compute that is very, very low. Now, in terms of a false, we're just going to run a code to make sure it's working. So we have our list. We're passing a 20. There is no number 20 within our list. So we're going to get a false. Now, this is essentially technically a worst case scenario because in order to find out if this was true or false, in order to make this part of the code to determine if we were going to fall down into the true or if we were going to jump out of the loop and return false, the computer had to go number 1, and then it had to go 2, 3, 4, had to sequentially go down this list to find that there's no number 20. So in the first run, matcher first 1, we only had to go through an element of 1 to find the true. In matcher list 20, we had to go through 10 different elements to find out that it's false. So technically this is a worst case scenario because we have to go through our entire data set to find out that there's no match. So that's a worst case because again, the entire list must be searched, n elements, O to the n, worst case becomes linear. This is a big O of 1, the constant, because again, 1's always going to be in the first index position within this particular list. Lastly, we're just going to talk on space complexity. So not only did we talk about how obviously there's a huge time complexity with big O notation and functions and algorithms, but there's also a space complexity. It's also concerned with how much memory space an algorithm uses. If you ever tried to do data work with AI, ML, DL on images, on ImageNet, or in any particular Kaggle piece, if you have a crappy GPU, it's going to come out and say memory error because you're trying to allocate, the algorithm is trying to allocate a certain amount of memory to the problem which it does not exist. So it's telling you I can't run this crap because you need more memory than what you have. So this notation of space complexity is the same, but instead of checking the time of the operations, we're checking the size of the allocation of memory. So in this quick example, we're just creating a function called memory, and we're putting it n equals 10. So then if we look at the code, it says for x in range n, again, n was 10, we're going to print memory. So we're going to print the string memory. So then we call memory 10. What's going to be our arguments? Actually, let me take that out because we assigned 10 to our argument of n when we ran the code. So of course, very complex code, right? It's going to print the word memory 10 times. But if you're looking at this loop, what we have here is this first piece is a time complexity. Because if n is 3, then it's going to run through this 3 times. If n is infinity, it's going to run through this infinity times. This is a time complexity. So this is O to the n. Because as n grows, so too will the time. This is a linear growth rate here. It's only one element, it's only one operation to run through to make that sufficient. Now for print memory, this is going to become a space complexity. And we have a big O of 1 for space complexity because memory is a constant. Meaning that it's not creating 10 versions of this, it's creating it once, and in terms of space complexity, it's just creating our one constant, it's running it 10 times. But the point is, this is the lowest computational intensive that we can deal with, because it doesn't matter if I made this as 100 and ran it. I'm not going to read through that for you, but It's not going to have any kind of effect on the big O in regards to space complexity, but will have effect of time complexity. So we have O to the n for the time complexity, which we already came to that conclusion. And the space complexity in memory, it doesn't need to store 10 versions of memory. It only needs to store one string, and that's going to be the constant. So again, in terms of if you said which one of these is more efficient, you would say the constant is more efficient than the time complexity. So in this particular code, if you were dealing with a larger piece of code and you had time complexities and space complexities, and if you had a space complexity of big O to the 1 and time complexity of big O to the n, if you had to manipulate some aspect of the code or to store something, you'd rather do it from a space complexity standpoint, because the computational intensive of that from the big O of a constant is much lower in terms of scalability and in terms of limits than the time complexity of big O n, because this, even though it's still linear, this is going to grow at a much faster growth rate in terms of computational intensive than the space complexity of a constant would. Now again, I don't expect all of this to sit within the first time that we're doing this, but that's why you have videos. You can go back and do this again and again, and we're just going to have more and more examples. And the whole point of this again was for algorithms, for also playing with Jupyter Notebook, but more so for algorithms, and then even doing with interviews, because as we get into ML and DL and AI, a lot of that is algorithm based. And even if you're doing something with NumPy or Pandas or scikit or sklearn, it's important that you understand what that algorithm is doing just from a complexity standpoint. So as you grow and you're trying to scale things, and if you're hitting limits or walls, you'll know what those limits or walls are caused from.